guys, this is Tyler with Kill Stress Designs. I wanted to tell you about a really cool project we've been working on. It's a solar race car chassis that was brought to the attention of us by the engineering students with the University of Southern California. And what they do is the students are designing a solar race car that they're going to compete with students from all around the world who've also designed solar race cars, and they're going to be racing them for over 1,000 miles. So we got to talking about their project, and I was pretty interested, wanted to figure out a way to help them out. One of the things that made it possible is the fact that we have this Siegmund welding table. If I didn't have this table, the way that I'd build this chassis would be to make a fixture out of sheets of plywood and lay out the orientation of the tubes, screw down stop blocks, and adjust that until it fit the dimensions of the CAD model, and weld up the two sides of the chassis. Then later combine them and square them up. That whole process is pretty time consuming, and they do that for if you're building like a home-built aircraft. They do fixtures like that quite often, but I didn't have time for that. So what I did is leverage this table's grid system and built on that. And that allowed me to fixture the entire chassis from just the individual tubes, set it up so it was a complete chassis in one shot, tack weld the whole thing in the jig, and actually weld out most of it still in the jig, pop it out to get to some parts that you didn't have access to. And the result is a really accurate chassis that's square, it's not warped, and it was fast. The next thing we did was developed a fixture based on the student's CAD model of the chassis and this actual table configuration. So all the CAD models for their entire product range is on the Siegmund website. So what we did is assembled this table arrangement, then brought their chassis on top of the table, overlaid it, and established our 0, 0 location, which would be, we used the side of the table and a set of prisms, which are just V pads, to locate the front of the chassis at a set height. And we have the chassis on the horizontal plane. Then we moved back in 500 millimeter increments with these squares to establish a bulkhead. The front of our chassis would be here, 500 millimeters back, we'd have our first bulkhead, another 500 millimeters back, we'd have the next bulkhead, and so on throughout the whole chassis. That gives us a vertical plane and a hole pattern that's on 50 millimeter centers. So what we did is, even when you have tubes coming through at an angle, you take this plane and you can use the cross-section of where those tubes are to create a dedicated fixture out of just thin laser-cut plate. And that way you can pin your fixture into place on these squares and cut a V-notch to hold that tube in exactly that position. There's no need to adjust the fixture. It's pinned in place. If you wanted to, you could repeat the fixture. You could tear down the whole setup, rebuild it the next week, build another chassis, and so on, and it's all modular components. The only dedicated fixturing we had is just that plate, so those can store in very little space. So for the dedicated fixtures, this is the 3/16 plate that we had laser cut, and the mounting surface for these toggle clamps to hold the tubes in position, I actually designed as a flat pattern, and then cut a kerf out to allow these to bend really easily with just a C-wrench, and then we can weld one side of it, and all the features that we need in order to bolt on a toggle clamp in exactly the location that we want it are there, already cut. So you cut a relief here, you can bend it, cut another relief here, bend it down, and that gives us our mounting surface. The plates themselves are pretty much identical throughout the chassis. The only place that they're different is where these holes are located in relation to this V. So it was really quick to design, and they just plop right into to the fixture. We've got a few different technologies which really make use of CAD. This table having an accurate grid system throughout the entire length of the chassis, and rigid fixtures. These are laser cut, so they're very accurate. But then the other thing that was going to consume a lot of time is notching all of that tubing. There was, almost 100 feet of tubing, and each section is pretty small, really pretty extreme angles to notch, and then holding all those tubes in alignment. So since there was already a chassis that's modeled really well in CAD, I showed the students how to establish the reference geometry in CAD to cut these slots and these tabs and notch the tubing so that you can send those files off to a company that offers 4-axis laser cutting, and in a couple of days you receive a pallet load of your chassis components that are ready to go, ready to weld with a little bit of prep. So the main frame components we held rigidly with our fixtures, but then the frame members that are for triangulation to make the chassis stiffer already have the tabs and slots cut in them, so we didn't need to put a fixture there. We can just tack it in place because how it's clocked to the other tubes is set, and its location along the chassis is set by how it fits into those slots. It just speeds up the fabrication a lot, and if you already have all these digital technologies that you can leverage for fabrication, you can do some really neat things really fast. Hope you enjoyed the video. If you want to see more, click subscribe. Thanks for watching.